Good morning. We're going to start our unit on inverse functions today. So today we're just going to look at how to find the inverse of a function, and sometimes you have to restrict the domain in order for the inverse of a function to also be a function. That is the goal for today. So the warm-up is on page 9 in your workbook. I'll have you open that up and try that, and then stop the video, come back, and we'll solve it together. Okay, so Ari received $100 as a birthday gift. Let's do our annotation. He received $100, decided to save money as well as save that money and add $20 of his own money each month. The total money Ari has saved can be estimated using this equation. Well, they just did our work for us there. X is the number of months. It's important to know what X stands for, and Y is the total amount of money saved. So X is months, and Y equals total money. Okay, so how much will Ari have saved after 6 months? So I can just use 6 as my X. And since I need to know the total amount of money, Y equals 20 times 6 plus 100. 20 times 6 is 120, so this would be 120 plus 100, $220. Okay, so how long will it take Ari to save $400? So now I know the total amount of money saved, so that's my Y value. And I'm going to have to solve for the number of months. So Y is 400, and I leave the X alone and solve for X. So now you're going to subtract 100, and you get 300 equals 20x. So 300 equals 20x. Opposite of multiply is divide, so we divide both sides by 20. The 20s go away on this side. 300 divided by 20 is 15, so X is going to be 15 months. And then the last question, suppose Ari decided to save $50 each month. The amount of money in his savings account after X months can now be estimated using a new equation. How long will it take Ari to save $400 with the new savings plan? So we still have Y equal to 400. So I go 400 where Y is, and then solve for X. Minus 100. 300 equals 50x. Divide by 50. And now 300 divided by 50 is 6 months. So Ari takes 6 months if he saves $50 a month. 15 months is a long time, but he's not putting away as much a month, so he just has to, it's just going to take longer to get the thing he wants to buy. Okay, so to start out, what is an inverse? It's the opposite of, thought of a function that undoes, don't say opposite, sorry. It undoes something that has already been done. In our everyday lives, turning off the faucet after it was on, that's the inverse function of turning it on is turning it off. Taking off your jacket or solving a puzzle. The inverse of algebraic functions, that's what we're going to talk about today, can be used to solve many problems if we know the dependent quantity but not the independent quantity, which is what we just did in the warm-up. The dependent quantity was our Y value, the amount of money saved. The independent variable in this case was the X value, the number of months. What if we switch those and we want to, so in the problems 2 and 3, we knew the dependent variable. So in this case, this became the independent variable and X became the dependent variable. I know that sounds a little confusing, so I'm going to show you what I mean. First, let's do a little review of what is a function. So a function is a relation. Remember, that's just a set of ordered pairs. A relation is a set of ordered pairs. A function is a relation in which every element or every x in the domain is paired with exactly one element in the range. So for every value of x, there's exactly one value of y. So in certain cases, the domain, or certain sets of ordered pairs are not functions. So for instance, something that's not a function would be this. This is not a function because if I go to this x value, it's paired with a y value here and a y value down here. So this is not a function. Whereas something like this, that bugs me, something like this is a function. Because if I go to this x value here, there's only one y value to go with it. Sometimes we use what we call the vertical line test to test whether something is a function or not, if you remember that from your early math days. This one touches the graph in two different places. This one only touches the graph in one place. So the vertical line test is a quick way to remember how to tell if something is a function. This is a function. Okay, so quick review of what is a function. Now, what is the lingo with a function? Well, we say we write f parentheses x. That does not mean f times x. That means this thing that we're looking at, this equation, is a function of x. It's used in place of y in an equation, and we say f of x when we use this notation. You don't have to say function of x, we just say f of x. Sometimes it's g of x, h of x, just depends on how the function is written. So it's used in place of y in an equation. So in other words, f of x equals 2x plus 1 is the same as saying y equals 2x plus 1. What is the output for the inputs -3, 0, and 1/4 in this function? Well, what this means is not f times -3, that means x is now going to be equal to -3 in my function. So I put the -3 where x is, and then I put it in the calculator or do your mental math. -2 times -3 is 6, 6 plus 5 is 11, etc. If x is 0, we write f of 0 equals -2 times 0 plus 5, which equals 5. Same thing for 1/4. -2 times 1/4 plus 5 is 4.5. So I've got a couple for you to try. So you can stop the video, try these 3, and then come back. This one is f of -2. That's going to be -4 times -2 plus 1. Well, -4 times -2 is 8. So 8 plus 1 is 9. B, f of 0 is going to be -4 times 0 plus 1. That's just going to be 0 plus 1, so that's 1. And C, f of 5, is going to be -4 times 5 plus 1. -4 times 5 is -20. -20 plus 1 is -19. All right, so obviously that's not what our lesson is about today because you learned that already, but we need to always look back and make sure we're on the same page. So, an inverse function. Now we're getting to the new stuff. An inverse function is a function that results when I switch my independent and dependent variables. Typically, that's your x and your y. So the dependent is usually the y, the independent is usually the x in a function. So find the inverse of the function f of x equals 3x minus 2. First of all, you're going to just take and instead of writing the f of x, we're going to put a y in that spot. So we're going to write this as y equals 3x minus 2. Step 2, switch the x and y, only the x and y. Don't switch the coefficients or the exponents. So you're just basically trading spaces. It's like if you traded seats in the classroom with somebody. It would just be you moving. Nobody else in your area would move just u. So if I'm doing that, I'm taking the I'm just switching where the x and y are. So now I have x equals 3y minus 2. So those two things just switch spots. The 3 stayed where it was, the minus 2 stayed where it was. Now solve for y. Okay, so I have x equals 3y minus 2. To get y by itself, I add 2 to both sides first. Remember, you undo addition and subtraction before you undo multiplication and division. So I have 3y equals x plus 2. Now I divide everything by 3, and I get 1/3 x. I'm going to go over here where I have more room. Plus 2/3 equals y, because this 3 divided by 3 is 1. Okay, so that's step 3. And step 4, replace the y with the inverse function notation, which is f to the power of -1 of x. So I write f inverse x equals 1/3 x plus 2/3. We write this 1/3 x because remember this is 1x over 3. So I can make that 1/3 the coefficient and put the x there. If you want to just leave it x over 3, I'm fine with that. This is your final answer. Now, you try this one, so stop the video, try this, and come back. So the first thing you'll do is replace the f of x with y. So I have y equals 2x plus 8. Now switch x and y. So x equals 2y. Why did I write a 9 there? Plus 8. 2y plus 8. Subtract. Now I need to solve for y, so I subtract 8 from both sides. Remember, undo addition and subtraction before you undo multiplication and division. So 2y equals x minus 8. Now I undo the multiplication by dividing by 2, everything by 2, and I get this equals 1. So this is y equals 1/2 x, and -8 over 2 is -4. And the last step, replace that y with the inverse notation. And we have our answer. There's the inverse of that function. Okay, so what does it look like when you look at the table of values for an inverse? Well, the first, the f of x, here is the function that we just did. The f of x equals 2x plus 8. So this, if x is -2, y would have been 4. Notice where that same point is over here, what happened to the x's and the y's? Well, they just switched. Well, let's think about that. What was our inverse function? 1/2 x minus 4. 1/2 of 4 is 2. 2 minus 4 is -2. And this one was 2x plus 8. 2 times -2 plus 8. 2 times -2 is -4. And that's 4. So see, notice how the x's and y's are just switching spots. If you did that for each point, it would work out that way. If you plug the former y value into your inverse function, you would get the former x value. So the x's and y's are just switching places. The inputs became the outputs. They were inputs here. Now they're the outputs. And vice versa, the outputs became the inputs. Okay, so the input values, let me do this in a different color. The input values, which were our x values, in the domain of the function, and the output y values are the range. From these tables, we can see that the input and output values are switched. Therefore, we can say that the domain of the function will be the range of the inverse. So that brings up a question, because remember, when we learn about domain and range, for every x value, there's exactly one y value. If that's true, then the relation is a function. But it doesn't say that you can't have repeated x values in the domain. So what if you do have repeated values? Well, then you have a problem with your inverse, because now you have repeats in the range, and we can't have that. So the domain and range are going to tell us whether the inverse is also a function. So remember at the beginning of the lesson, we talked about the vertical line test. To tell if something is a function, we can use the vertical line test. So we looked at the circle, and that was not a function. Another one that might not be a function is a quadratic equation. So let's look at a couple of these. So if you can draw, what I was going to talk about is the horizontal line test. It's kind of the opposite of the vertical line test. So if you can draw a horizontal line, which is left to right, if you can draw a horizontal line so that it intersects the graph exactly once, then that function we say is 1 to 1. 1 to 1. It's a function when it's a function, it's a function when it's an inverse function. Is the function x cubed 1 to 1? Well, let's look at some horizontal lines. We know it's a function. It looks like it is a function, right? A 1-to-1 function, because it passes the horizontal line test. Now let's look at the quadratic function. Is that 1-to-1? Well, I just crossed the graph twice there. But that doesn't pass because it can only cross the graph once. So this is no. I don't know why I always put exclamation point with no. How could we make this a function? Well, it had a 1-to-1 function. It can only cross the graph once. So if I cross it once here, I can't cross it here. So what if I just got rid of this whole piece of the graph and just had this piece of the graph? Cut the graph in half. Where is that line that I cut it? Well, it's right in the middle. We call that the line of symmetry. At the line of symmetry, if I cut the graph in half, I just have, remember, a quadratic function is symmetric, so it's exactly the same on one side as the other. So I still have half the graph. So at the line of symmetry, or the vertex, I cut it in half, and I still have half the function. And I can say that that half is 1-to-1. So I know that point of the vertex, that x value of the vertex, is where I want to restrict my domain. If I say the x values are all greater than or equal to 0, I now have half the function, right? There, you have half the function. We got rid of the half here. Now, if I draw a horizontal line, it passes the horizontal line test because it's not crossing on this side. So we could take half of the domain out of that function. Remember, the domain normally would be all real numbers. But in this case, in order to make the function 1-to-1, if I take out all the negative numbers, in this case, then this thing is 1-to-1. So we restrict the domain by taking out half the domain, and we're good to go. We have a 1-to-1 function. So if a function is not 1-to-1, restrict the domain. And so let's just talk about domain and range again, because I know that's very confusing. It's kind of an abstract thing, and a lot of people still are struggling a little bit with it. So this is a little way to remember what domain and range mean. Domain is your input values, your x values, and your range is your output, or y values. Okay, so I'm going to talk about what the domain and range would look like normally, and then if we have to restrict it. And we saw that well, we didn't see, but what if I did the horizontal line test on a linear function? Linear function. In other words, we're going to say this is y equals ax plus k. I'm not writing it mx plus b because I want it to look like all the ones I'm going to write here. A linear function, remember, it looks like this. That's going to pass the horizontal line test. So this is a one-to-one function, so we don't have to restrict the domain, and the domain is always going to be from negative infinity to infinity. X can be all real numbers. And the y's are also going to be all real numbers. Okay? So the linear function, we don't have to restrict. What about a quadratic function? What about a quadratic function? Quadratic function, we write y equals a times x minus h squared plus k. Remember that little note card, the notes we did at the very beginning, we wrote our absolute value function in the standard form. It's the same for quadratic, or cubic, any other kind of function. So in a quadratic function, if we write it in vertex, we call this vertex form, we can see that the x value, well, I don't know if you remember this, but the x value at the vertex is h, and the y value at the vertex is k. So the vertex is going to be hk. If the vertex is hk, and remember I want to restrict my domain at the vertex, I want to restrict my domain at this h value. So normally the quadratic function would have the same domain as the linear function. But if we restrict it, because we know that it's not one-to-one, we have to say that the x's are going to be greater than or equal to whatever that number h is. We don't have to restrict the range, but we know also in a quadratic that the range has either a minimum or maximum value depending on whether it's a upward facing or downward facing parabola. And that's based on this number a. Remember, if a is a negative number, then the parabola reflects over the x-axis. So the a is positive, then our domain, or our range, the y's are greater than or equal to whatever that number k is on the outside. That tells you your range. And if a is negative, the y's are going to be just less than or equal to whatever that number k is. It's either going to be a minimum value in your range, or k will be a maximum value in your range. So when we restrict the quadratic, we always look for this number h, and that will tell us the restricted domain. Now let's think about a radical function, because we're also going to look at those today. Radical function, we can write it in the same form as the quadratic, so a, except now I'm going to do a radical symbol, x minus h plus k. Now this one I don't have to restrict, because if you remember what this looked like, the parent function looked like this. So that's going to pass the horizontal line test. So I don't have to restrict the domain, but I do have to remember that there's a lowest point in that domain, because remember, you can't have we're talking about real numbers, so you can't have negatives under that radical. So x minus h would tell us this number, the lowest x value, and k would tell us the lowest y value. So in general, your domain for a radical is always going to be x is greater than or equal to h. And the range would be the same as for a quadratic. If a is positive, y is going to be greater than or equal to k. And if a is negative, y is going to be less than or equal to k. So for now, that's how we're going to show restricting the domain for a quadratic function. So let's try it. It makes a lot more sense when you actually see it in action. So the domain and range of all of these, or of the quadratics, would normally be negative infinity to infinity. And the range is going to be based on this number. So y is greater than or equal to negative 1, because this number 2 is positive. That's my a. And this same thing for this quadratic. The domain is still negative infinity to infinity, because I'm not saying let's make it 1 to 1. I'm just saying what is the domain for this. And the range is going to be, we have a negative value here, so y is going to be less than or equal to 1, because it's going to be upside down. What about the radical function? Well, the domain starts at this number. This is a positive function, so I can follow the rules for positive a value. So x is going to be greater than or equal to negative 3, and y is going to be greater than or equal to 2. So if they're not 1 to 1, what are the restricted domains? So I know number 1 is not 1 to 1. So now if I restrict that domain, let's see what this must look like, because I don't have any parentheses here. So that means my h is just 0. So if you've got an x squared and no parentheses, this number is not your h. That's always your k. The one that doesn't have your constant term is your k. Your x, if you just have an x squared with no number added or subtracted to it, no parentheses, then your h is 0. So h is 0, k is negative 1. The domain of this one, if I restrict it, is just going to be x is greater than or equal to 0. And number 3, I had negative x minus 2 squared plus 1. In this case, h is equal to 2, because remember it's x minus h. If this were positive, then that would make this negative. H is 2, so x has to be greater than or equal to 2. Now you're going to go to your book to page 13. Got a couple examples. The first one is about Lana. Lana is driving home from her friends. She's driving at a steady speed, and her distance from her home in miles can be represented by this function. X is her driving time, and the distance from home is the f of x. So x is her time. I'm sorry. X is her driving time, and y is distance. So now I want the inverse function. So this is for f of x. For f of x. We want to show the inverse function so that when in hours Lana will be x miles from home. So now if I'm finding the inverse function, they're saying now my x is not time, x is distance. Well, that makes sense because we know the domain and range switch places, so what they mean is going to switch. So now when I find the inverse, x is going to be the distance from home. That my independent variable will be distance from home, and my dependent variable will be time. Okay, so the first step is determine if this is a one-to-one function. Well, it's a linear function, so if you put it in your calculator and look at it or plot the points, you would see it is 1-to-1, negative 40x plus 15. So y equals negative 40x plus 15. I don't know what my graph is set on. Zoom 6. So we see if we draw horizontal line through that, it would pass the horizontal line test. So number 1 is yes, it is 1-to-1. Number 2 through 5, I'm just going to do it all at once. 2 through 5, I need to rewrite this function as an inverse. So let's write it y equals negative 40x plus 15. Replace the f of x with y. Now switch your x and y. And solve for y. divide by negative 40. We get negative 1 over 40. And this is going to be positive. And if I reduce 15 over 40, it reduces to 3 over 8. And that would be y equals, but since we found the inverse, that's your answer. So there's the function that you would use. Now x is her distance. The answer would give us the time. So if I plug in 80 for x, it would be, I would get an answer how long it would take her. Okay, number 2, a high school is selling tickets to a school play. The school is using the money earned from selling the tickets to pay for the play. Any extra money after expenses will be profit. The profit in dollars can be represented by the equation P of x equals 12x minus 600. So right now I know profit, P is profit. My y is, my dependent variable is profit. X is the number of tickets sold. Number of tickets. Okay, so if x is the number of tickets and y is the, so I write this y equals 12x minus 600, and I switch the x and y and solve for y. So I have 1/12 x plus, and 600 divided by 12 is 50. That's going to be my inverse. So now this will be the number of tickets, and this will be the profit. Find the inverse of f of x equals 4x squared. So now we're going to have to restrict the domain because we have a quadratic function. So in other words, this is f of x equals 4 times x minus 0 squared plus 0, because you don't have a h or a k. So all we need to do is find the restricted domain, and that's x is greater than or equal to 0. So we make this y, and we'll go back to 4x squared. Switch the x and y. Now what do I do? Well, I don't have any plus anything, so I don't have to add or subtract, but I do have a coefficient here I don't want here, so I'm going to divide by 4. So now I have x over 4 equals y squared. Well, when I square root both sides, I get square root of x, and the square root of 4 is 2, so over 2 equals y. Because remember, when you do a square root, this is the same thing as saying square root of x divided by the square root of 4. That's what that means. Okay, so now I can rewrite this f inverse of x equals square root of x over 2. And the domain would now be the range would now be the domain. We're going to talk about that later in the week. Okay, you're going to go to page 13 in your book, and you're going to try 1 through 10. And if you need any help, I have the solutions done in my book, so you're welcome to stop over. If it's third block, I'm giving a test, so just be respectful.